Hello everyone. The title of my presentation is a new approach on the modeling and control of complex biological systems. The outline of my presentation is as follows. In the first section, we give some definitions regarding three different fractional operators. In section 2, we introduce a new mathematical model for a dengue fever outbreak. In section 3, we investigate a numerical method and discuss its stability and convergence analysis. In section 4, we provide a state feedback control idea as an insecticide approach. Next, we give some simulation results to verify the theoretical analysis. And finally, we close this presentation by some concluding remarks. Now, we introduce three different fractional operators with singular and non-singular kernels. For the singular operator, we consider Caputo fractional derivative, while for non-singular ones, we take into account Caputo-Fabrizio with an exponential kernel and ABC with a Mittag-Leffler kernel. Concerning Caputo derivative and its corresponding fractional integral, we provide equations 1 and 2 respectively. The Laplace transform of Caputo derivative is also given by equation 3. With regard to Caputo-Fabrizio differential and integral operators, we have equations 4 and 5 respectively. Also, the Laplace transform of Caputo-Fabrizio differential operator is computed by equation 6. Regarding ABC differential and integral operators, we have equations 7 and 8 respectively. In these equations, the function b represents the normalization function and e is the Mittag-Leffler function given by equation 9. The Laplace transform of ABC differential operator is also computed by equation 10. In the following, we try to model a dengue fever outbreak which happened on the Cape Verde Islands in year 2009. To describe the dengue fever epidemic model, the human population is decomposed into three compartments as susceptible, infected, and immune individuals. In reference 4, the dynamics of the dengue fever have been given by the following system of ordinary differential equations. In these equations, the variables SH and IH denote respectively the number of susceptible and infected humans, while RH represents their population having acquired the immunity against the infection. The disease spreads by the bite of female mosquitoes. Two groups are taken into account for the female mosquitoes population as susceptible and infected ones. The number of infected female mosquitoes is denoted by IM, while the population of susceptible ones is signified by SM. The expressions NH and NM describe the total number of humans and female mosquitoes respectively, which are constant and computed by the following equations. The interpretations of the remaining parameters used in equation 12 as well as their values are also given in table 1. Note that here we just consider the female mosquitoes since the male ones do not bite humans and hence they have no impact on the disease dynamics. In addition, for the female mosquitoes, the only blood source is human, hence we have M equal to 0. The initial conditions for this system are also considered as in equation 13. This reflects the fact that initially the mosquitoes population was uninfected, and traveling unhealthy humans imported the virus into the ecosystem. Why fractional? Although the model 12 describes some basic behaviors of the ecological system under consideration, the authors in 5 showed that the solution of integer order model does not provide a good match with the actual number of infected humans. On the other hand, many scientists have shown that the fractional models are in better agreement with the experimental data than their integer order counterparts. Therefore, we will try to modify the dengue fever model 12 by using the new aspects of fractional calculus in order to provide more precise results close to the real data. To do so, we can replace the integer order derivatives in equation 12 by one of the fractional derivative operators described in section 1. Note that mosquitoes and humans may not behave in the same way. Hence, we select two different fractional orders Qm and Qh for the equations presenting the dynamics of mosquitoes and humans respectively. In addition, some parameters in the system model are modified to ensure that the right and left-hand sides of the resultant fractional equations have the same dimension. Consequently, we provide equation 14 as a fractional model of dengue fever outbreak under consideration. As QH and QM go to 1, the fractional system 14 tends to the classic integer model 12. In addition, we can prove that the system 14 is positively invariant in R5+. That means no population goes negative. In the next section, we construct a numerical scheme to approximate the solution of the fractional dengue fever model 14. To develop the numerical scheme in terms of Caputo-Fabrizio, and ABC, we rewrite equation 14 in a compact form as in equation 15. In this equation, x denotes the vector of variables, x0 denotes the initial condition, and f is a real-valued continuous vector function satisfying the Lipschitz condition. Applying the integral operator 2, 5, or 8 to equation 15, we provide equation 17. To propose the numerical scheme, we choose a uniform mesh with the time step size tau. Also, we denote xn as the approximate solution of x at Tn, where Tn is equal to n tau. According to the definition of the integral operator 2, we obtain the integral 18. On each subinterval tk and tk plus 1, f is approximated by a piecewise linear interpolation polynomial as in equation 19. Inserting the above approximation into equation 18, we obtain equation 20. The coefficient in equation 20 is defined by equation 21. Finally, we can provide the fractional trapezoidal method for equation 17 in the sense of Caputo as in equation 22. In order to derive the trapezoidal formula for equation 17 in the Caputo-Fabrizio sense, we follow the same procedure as in the Caputo sense. Therefore, we obtain the Caputo-Fabrizio fractional trapezoidal method as in equation 24. Finally, we can provide the fractional trapezoidal method in the ABC sense as in equation 26. Now we analyze the stability and convergence of the numerical schemes 22, 24, and 26 in the sense of Caputo, Caputo-Fabrizio, and ABC respectively. Theorem 1 says the numerical schemes 22, 24, and 26 are conditionally stable. Also, Theorem 2 states that the numerical schemes 22, 24, and 26 are conditionally convergent. In this part, we consider an insecticide campaign to kill the adult mosquitoes. The level of this insecticide is modeled by inserting a new control parameter to our model. Then we try to design a linear state feedback controller to make the disease-free equilibrium point asymptotically stable. To do so, we consider the following fractional control system, in which P is the state feedback gain constant. Our objective here is to find a stabilizing gain control P which ensures the asymptotic stability of the disease-free equilibrium of the closed-loop system 28. In order to design a stabilizing controller, the parameter P should be selected in such a way that the following condition is satisfied. As can be seen, the parameter R0 follows a decreasing manner as the control gain P increases. This fact guarantees the existence of a stabilizing controller satisfying R0 less than 1. Here, a comparative study is carried out between the simulated curves of the fractional model 14 and the real data for a dengue fever outbreak that happened on the Cape Verde Islands in year 2009. Simulation and comparative results are shown in figures 1 to 5. As can be seen from figure 1, the simulated curve of Caputo derivative model better approximates the real data than the classical integer model. In addition, a particularly better approximation is obtained by using Caputo-Fabrizio operator versus the classical solution as shown in figure 2. Furthermore, figure 3 indicates that the fractional model with ABC operator fits the real data more accurate than the pre-existent classical model. However, as can be seen from figure 4, the simulations within Caputo-Fabrizio operator is close to the real data in the early stage of the epidemic, i.e., up to the peak of the number of infected humans, whereas ABC operator captures the qualitative features of the real data for the later part of the time interval. Hence, it turns out that a combination of ABC and Caputo-Fabrizio fractional models is the best candidate in our case, according to the real experimental observations. In this case, we consider the changing point between two models in the time domain as the intersection of two plots associated with Caputo-Fabrizio and ABC. The final hybrid simulation compared to the experimental measurements is depicted in Figure 5, which illustrates surprisingly good results. Considering this hybrid model, we applied the state feedback control strategy provided in previous section to make the disease-free equilibrium point asymptotically stable. In this case, we selected the state feedback gain constant as p equal to 0.9, 0.5, and 5 respectively for the first and the second part of the hybrid model to satisfy the sufficient stability condition 29. Computational investigations related to the human population with control are displayed in Figure 6, which verify the efficiency of the proposed insecticide campaign stabilizing controller. Now we give some concluding remarks to close this presentation. In this research, we proposed a new approach for the modeling of dengue fever outbreak by using its new formulation in fractional calculus. The efficiency of this new framework was examined by using a set of real data registered by World Health Organization. The proposed model consisted of a new hybrid structure involving the fractional operators with the exponential and Mittag-Leffner kernels. For the purpose of implementation, a new and efficient numerical method was developed by extending the trapezoidal method in fractional sense, and its stability and convergence were proved. Comparing the numerical experiments with the real data verified that the proposed hybrid fractional framework can describe the reality very well in the whole of the time interval, better than the pre-existent integer and fractional order models. In this study, we also considered an insecticide campaign as a state feedback control strategy. Simulation results showed that the suggested controller has the capability to prevent the outbreak and reduce the number of infected individuals. Here you can see the references of this presentation. Finally, I would like to thank you very much for your attention.